Hello, here's just a quick little video for you to review the temperature scales and to take a look at the atom. What are the parts of the atom, where they located, what are their charges, and who discovered them. And so just wanted to quickly remind you about those temperature scales. We do have 3 temperature scales we'll be using. Fahrenheit, I know you're familiar with. And Celsius is what we're typically going to use in chemistry, and that is our metric temperature scale because it is based on water. Water freezes at 0 degrees Celsius and boils at 100 degrees Celsius. And then our more scientific temperature scale, kelvins. And so you want to be able to convert between those measurements. So if you have 25 degrees Celsius and you added 273.15, you're going to come up with 298. So you'd almost have to round that using significant figures to get to 2 significant figures. With that same 25 degrees, multiply by 1.8, add 32, and you're going to come up with 77 degrees Fahrenheit. That 25 degrees Celsius is equivalent to 77 degrees Fahrenheit. What I would suggest is that you take a moment, pause the video, and practice these conversions. And here's the answer, so be sure to check your work. And now I'm ready to move into chapter 2 with atoms. And so let's go ahead and get started. Some of the items that we're going to cover in chapter 2 are listed here. You've probably already read about those, or you should be reading about those now. And so I just wanted to kind of summarize a couple of these discoveries and give you a little bit of information that I think will help you with the homework for this week. Of course, this little cartoon of the atom does kind of capture what the atom looks like. And we're going to be talking about that right now. And the history of the atom goes back actually to the ancient Greeks. The ancient Greeks were the ones that kind of first came up with the idea of the atom. They weren't scientists. They were just philosophers who were sitting around thinking about things and talking about things. And they sat down and they thought and they talked that, it's reasonable that if we have this sand, at some point in time, we're going to be able to separate it and come to the smallest piece. And we're going to call that smallest piece indivisible. And their Greek word for indivisible was atomos. And so that is where our idea of the atom came from. Now, of course, and there were a couple of ancient folks that you should be aware of. Aristotle, I'm sure you've heard of. And it was actually Democritus who came up with this idea. And Aristotle opposed it. And at that time in Europe, they were having a lot of issues. And so people kind of forgot about science for a while. It was actually thousands of years before this young man, John Dalton, brilliant, principal of his school at age 12, went back to the ancient Greeks and was like, I think they were onto something. And he was an excellent experimenter. He didn't just sit around and think about things. He actually experimented. He would take water, measure its mass, evaporate the water, measure the vapor to confirm that, in fact, he still had the exact amount of water that he had evaporated. And he actually came up with the idea that if we have hydrogen atoms, that all hydrogen atoms are alike, but they're a little different than oxygen atoms. And so he really revived this idea in the late 1700s. And then we come to J.J. Thomson. And at this time, they were playing with these little cathode ray tubes and electricity. And he found that if he took different metals and sent electricity through these tubes that didn't have anything in them, that he could see a beam that he then figured was negative because he used a magnet. You can see this beam was attracted to that magnet. And so J.J. Thomson is credited with discovering the electron with his cathode ray tube. Of course, he figured that the electrons were negatively charged, although we know atoms are neutral, so those negative charged electrons must equal something else. And that's when Rutherford came along in the early 1900s, and he was working with J.J. Thomson's idea of the atom. And this is a little picture of his model of the atom, often called the plum pudding model, because he thought there were little electrons there embedded in a sea of positivity. But anyway, Rutherford came along, and what Rutherford did was shoot a helium nucleus, sort of like a bullet, very small, and I'll show you how to write this in just a little bit, had a mass of 4 and 2 protons. So this helium nucleus, because there's no electrons, is positively charged. And what he did was he shot this at a piece of gold foil. Now, many of these particles actually went through the gold foil, but every once in a while, like 1 in 10,000, would bounce back. And so he started thinking, what is it hitting? It must be hitting something that's positive because my helium nucleus is clearly repelling from this item. And he is now credited with having discovered the small, positively charged, dense nucleus of the atom with his gold foil experiment. And so he summarized or concluded that most of an atom is empty space, but there's a small, dense, positively charged piece in the center that we now know as the nucleus. His student, and so he kind of reorganized the atom into 2 distinct regions, which we still use today. The nucleus, which has a positive charge, and the electrons, which are out there with their negative charge. His student, who actually had done the counting, Chadwick, went on then to discover the neutron, which is also in the nucleus. And so now we have our modern view of the atom. It has a nucleus with 2 particles, the protons and the neutrons. And it has the electron cloud on the outside. The positive protons in the nucleus equal the number of negative electrons on the outside, and so our atoms are neutral. All the mass of our atom is in that small, dense, positively charged nucleus that Rutherford discovered with his gold foil experiment. And in 2013, we have the first picture, actual photograph with a quantum microscope of the atom. And you can see this confirms J.J. Thomson's discovery of the electron and Rutherford's discovery of the nucleus, because we have this small, positively charged, dense nucleus in the middle and the electrons out here. All right, whose model would you say this is? Hopefully you were thinking that's Thomson's model. That looks like plum pudding. How about whose experiment? That is Rutherford's experiment. And what did he discover? Of course, he discovered the nucleus. All right, and so that brings us to our subatomic particles, 3 particles of the atom, the proton, the neutron, the electron. And so you're going to want to know and review the symbols for those and the charges. Because the charge of the proton is exactly opposite the charge of the electron, we often just call the protons a charge of +1 and the electrons a charge of -1. Notice the mass of the proton and the neutron are 1, and we often think of the electron as having virtually 0 mass because it is so small, especially if you start thinking about significant figures, compared to the proton and the neutron. So when we're taking a look at the atom, the most important number for the atom and the item that identifies an atom is the atomic number, which is the number of protons. Now, of course, if the atom is neutral, that is also going to be our number of electrons. If our atom is not neutral, like equal numbers of protons and electrons, then it's going to be an ion. And the periodic table is ordered by this number of protons, the atomic number. The mass number, the mass of the atom, so that's our protons and our neutrons in the nucleus, is also listed on our periodic table. And so you'll want to look at those masses. And that mass is not the mass of every atom. That is the average atomic mass. And I've got a different video to send you to work on calculating the average atomic mass that you see listed on that periodic table. And so basically the periodic table then has all the information that you are going to need. All right, and so you'll probably want a periodic table for this next little part because I'm going to show you how to take the information from the periodic table and write it in a shorthand way. And so the first thing we do is we would take the element symbol and replace it by X, the mass number at the top, so we're kind of flipping it from the periodic table, and the atomic number, that's again what identifies the atom, it's our number of protons, at the bottom. And so if we take these two values, the mass minus the atomic number, that's going to give us our number of neutrons. And so just doing a little subtraction there will give you that number of neutrons. And that's really the only way that you can find the number of neutrons, is by doing that subtraction. All right, so let's take a look at carbon, for example. Now, if you look at your periodic table, you're probably going to see that the mass of carbon right here is something like 12.011. That's what my particular periodic table I have that I'm looking at has. Yours may be something a little bit different. And so I'm going to write it with my symbol for carbon here, my mass number right here, and my atomic number right down at the bottom. Now, all carbon atoms are always going to have an atomic number of 6. That's our number of protons. That's what identifies it. And if I do this little subtraction here, I can figure out that carbon does have 6 neutrons. And that's really the way to figure that out. Now, that's only this particular carbon atom. Other carbon atoms may have a mass of 13 or 14. And so they're going to have different numbers of neutrons. And those are the atoms that we call our isotopes. And so there you go. So let's look at oxygen. Right? So how many protons does oxygen have? Hopefully you're thinking 8 protons. What's the mass of this oxygen? Well, it's roughly 16. And so this is the average atomic mass. And so we're going to round it to 16 because that's going to tell us that most oxygen atoms have a mass of 16, which means that most oxygen atoms have 8 neutrons. And so if I wanted to write this in oxygen atom in that shorthand way, I would write it just like this. And so you can see that we've got 8 neutrons, 8 protons, and that's why our mass is 16. Now, as long as it's an oxygen atom, it's also going to have 8 electrons. And so just a little reminder that the periodic tables don't tell you the mass of each individual atom. They've sampled thousands of atoms, and those are the average masses. You will need to be able to calculate the average atomic mass, and I do have a shorter video for you about that. All right, so let's take a look at this particular magnesium atom. How many protons? Well, that's where I'd need my periodic table. Magnesium is always going to have 12 protons. And so I could put that atomic number right down here. And you can see that this particular magnesium atom is also going to have 12 neutrons. I'm also going to guess, because it doesn't have a charge, that it has 12 electrons. All right, how about this zirconium atom, how many protons? Hopefully you're thinking 40. How many neutron or electrons? 40, as long as it's a neutral atom. Now, it is a metal, and metals are always going to want to give away electrons to become positive ions. So just something you should be aware of. How about neutrons? Well, this particular atom has a mass of 91, so I simply subtract and get 51 for my neutrons. Let's try another one. Oh, now this one we've got an ion. This is not a neutral atom. And that should say N there, not Zr. So let's fix that. How many protons? Hopefully you're thinking 7. Yes, because that is our atomic number right here. That's how we're going to identify that nitrogen atom. Electrons? So this 3 plus here means that it has gained 3 negative charges. So that means that it's going to have 10 electrons. And of course, it's going to have 8 neutrons because 15 minus 7 is 8. Now, what isotope of nitrogen is most common? Well, if I look at my periodic table, I see that the average mass for nitrogen is 15. So that means it would be nitrogen with a mass of 14. So it would have 7 neutrons, would be the most common. This atom of nitrogen is just a different isotope. And you could actually say that they are isotopes of each other. Nitrogen 14 and nitrogen 15. All right, so let's take a moment. Did we accomplish what we needed to today? Can you convert temperature measurements without changing the actual measurement and maintaining your number of significant figures? I hope so. All right, so if we have 0 Kelvin, see if you can match these up really quick. Or 0 Celsius, Kelvin, and 100 degrees Celsius. Obviously, 0 Celsius is the same as 32 degrees Fahrenheit. That's the temperature water freezes. Kelvin is our scientific temperature scale. Degrees Celsius plus 273. And 100 degrees Celsius is where water boils. Can you identify the parts of the atom and their characteristics? Hopefully you're thinking those 3 subatomic particles are our protons, neutrons, and electrons. And the charge of a proton is +1. Neutrons have no charge, and electrons have a negative charge. And can you identify the people who discovered the various parts of the atom and what they did? Who discovered that most of an atom is open space with the gold foil experiment? Hopefully you're thinking Ernest Rutherford, and you are exactly right. I hope this helps you until I see you again.